Ever tried to piece together a 3D puzzle with missing pieces, and some wrong ones mixed in? That's basically what scientists face when working with Euclidean distance matrices, those tricky tables that track distances between points in space. But here's the good news. A new method is changing the game, making it easier to rebuild missing data and fix errors. Let's break down how it works. So what's an Euclidean distance matrix, or EDM? Imagine you're mapping a city, but some roads are erased and others have the wrong lengths. An EDM is like that map, except it's a table of squared distances between every pair of points. If you have 10 points, there are 100 entries. But in real life, this data is often incomplete or full of errors. Maybe a sensor failed, or a measurement was miscalculated. Traditional methods struggle to fix this, leading to blurry or wrong results. The breakthrough here. Instead of working directly with the EDM, the researchers use something called a gram matrix. Think of it as a simpler version of the same data, focusing on how points relate through angles and overlaps, not just distances. The gram matrix is lower rank, meaning it has less complexity, making it easier to handle missing or noisy data. But here's where it gets clever. They didn't just use the gram matrix directly. They employed a technique called the dual basis approach, which is like using a specialized lens to zoom in on the most important parts of the data. Imagine you're trying to find a needle in a haystack. This method helps you focus on the areas where the needle, or the correct data, is most likely to be. By transforming the problem with non-orthogonal bases, they could isolate the critical distances between known anchor points and unknown target points, ignoring the rest. Their algorithm, RoDEoDB, is designed to handle sparse outliers. Think of a few wrong distances in your city map, like a bridge listed as 10 miles instead of 1. RoDEoDB identifies these errors and corrects them, reconstructing the true layout. It combines two powerful ideas: Nyström approximation, which fills in missing data by leveraging patterns, and alternating projections, a technique that refines estimates by bouncing between constraints like low-rank structures and observed measurements. What makes this approach revolutionary? It doesn't need the full EDM. Instead, it works with partial structured data, like distances between anchors and targets. This is a game changer for real-world applications. In sensor networks, anchors might be GPS devices, while targets are unknown nodes. In molecular biology, anchors could be known atoms, and targets are the ones we're trying to locate. The results? On tasks like sensor localization and protein structure prediction, RoDEoDB outperforms existing methods, even when up to 20% of the data is corrupted. The theory behind it guarantees exact recovery under certain conditions, making it both practical and mathematically sound. So why does this matter? From smarter GPS systems to faster drug discovery, this method is paving the way for more accurate and reliable data analysis. It's a reminder that sometimes, the best solutions come from looking at problems from a different angle, literally. Thanks for watching. If you want to dive deeper into the math or see how this applies to your favorite tech, hit that subscribe button. Stay curious, and we'll see you in the next video. Ever wondered how scientists figure out the exact positions of stars in the sky, or how sensors in a room know where they are? It all starts with a clever math tool called a Euclidean Distance Matrix, or EDM for short. Think of it as a digital map, where every number tells you how far apart 2 points are. But here's the twist. These matrices are tricky to work with, especially when the data is noisy or incomplete. Today, we're diving into the math that keeps these matrices reliable, and why it matters for everything from GPS to protein folding. So what makes EDM so special? Imagine you have a bunch of points in space, like sensors in a room. An EDM is just a table that lists the square distances between every pair. But here's the catch. If one distance is off by even a little, the whole matrix can go haywire. Traditional methods try to fix this by assuming the EDM is valid, but real-world data is rarely perfect. That's where the gram matrix comes in. Think of it as a simplified version of the EDM that focuses on relationships between points, not just raw distances. By leveraging the gram matrix's lower-rank structure, researchers can bypass the complexity of the full EDM. The dual basis approach then acts like a filter, isolating the most critical data points. This is where RoDEoDB shines. It uses Nyström approximation to fill gaps and alternating projections to refine estimates, all while handling outliers. The result? A method that's both mathematically rigorous and practical for real-world problems. From reconstructing molecular structures to improving sensor networks, this breakthrough shows how rethinking foundational math can unlock new possibilities. Stay tuned for more deep dives into the algorithms shaping our tech-driven world.